Hey everyone, if you're serious about crushing NEAT, you know that the NCERT textbook is your Bible. So today we're going to do a deep dive into one of the most critical chapters in organic chemistry, hydrocarbons. Think of this as your strategic guide to absolutely hacking this chapter, using nothing but the NCERT line by line.
So let's kick things off with a big question you're probably asking yourself. How in the world do you actually score full marks on hydrocarbons just by using your textbook? It sounds easy, right? But the real trick is knowing what to focus on. And that's exactly what we're about to break down.
So here's our game plan, our blueprint. First, we'll build the basic framework. Then we'll move step by step through alkanes. Then into alkenes, which is all about the addition game. And then we'll cover that crucial link from alkynes to aromatics. And we'll finish everything off with a high-yield revision map to make sure all these concepts stick. Let's get into it.
All right, first up, the hydrocarbon framework. We're starting from scratch here, building our knowledge from the ground up, exactly how your NCERT wants you to.
Okay, the book starts with the absolute basics. What are hydrocarbons? Super simple, really. They're just compounds made of carbon and hydrogen. That's it. The whole chapter is built on how we classify them into three main buckets: saturated, with all single bonds; unsaturated, with double or triple bonds; and then that special group, the aromatic hydrocarbons. This is our foundation.
Let's jump into our first big category, alkanes. We're going to crack the secrets of what the NCERT specifically calls paraffins. And that name is a huge clue.
So, alkanes are these saturated hydrocarbons, and their general formula is CnH2n+2. But why the weird name paraffins? Well, it actually comes from Latin, parum affinis, which literally means little affinity. And that name is perfect. It tells you their #1 personality trait. They're pretty unreactive, or inert. They don't want to react with much, and that's a key property to remember.
Now check out this table. It's straight from the data in your textbook, and it's a gold mine. Just look at the boiling points for the isomers of pentane. You've got the straight chain, pentane, and then as you start adding branches, look what happens. The boiling point drops. A lot. This isn't random. It's a super predictable trend that NEAT absolutely loves to ask about. So the big question is, why does this happen?
And boom, here's the answer. This is a direct quote from your NCERT. You need to highlight this, circle it, whatever you need to do to memorize it. This is your go-to explanation for any assertion-reason question on this topic. As you add more branches, the molecule gets more spherical, kind of like a ball. This means less surface area for molecules to stick to each other, which means weaker forces and a lower boiling point. Simple as that.
Okay, let's talk about a key preparation method, the Wurtz reaction. Now here's the deal, and this is the part you cannot forget. This reaction is fantastic for making symmetrical alkanes. You know, the ones with an even number of carbon atoms. If you try to make an alkane with an odd number of carbons, you just get a big messy soup of different products. NEAT knows this, and they will try to trap you with it. So remember, Wurtz is for even.
The chlorination of methane. It's a classic free radical mechanism, and it happens in 3 clean steps. First, initiation. Light comes in and splits a chlorine molecule into 2 angry radicals. Then, propagation. This is the chain reaction part, where the radicals start attacking methane. And finally, termination. Now pay close attention to this last step. See how 2 methyl radicals can combine? What do they form? Ethane. This directly explains why you get ethane as a byproduct, which, by the way, is the answer to a question right in your NCERT exercises.
All right, let's switch gears and move on to alkenes. Now that double bond with its weak pi bond changes everything. Their whole world is about addition reactions. That's why I call it the addition game.
And you can't talk about alkenes without knowing this rule. This is maybe the most famous rule in the whole chapter, and it's quoted word for word from your NCERT. When you add something like HBr to an alkene that isn't symmetrical, the negative part, in this case the bromine, is going to go to the carbon that has fewer hydrogens. Why? Because that path creates a more stable carbocation intermediate.
But wait, just when you think you've got it figured out, here comes the big NEAT trap. It's called the peroxide effect or the Karash effect, and it does exactly what you'd think. It flips the rule completely. Now you get Anti-Markovnikov addition. But, and listen up, because this is absolutely crucial, this exception applies only to the addition of HBr, not HCl, not HI, only HBr. Got it?
This slide just lays it all out, crystal clear. Look at the left. No peroxide. You follow Markovnikov's rule, you get that more stable secondary carbocation, and boom, your product is 2-bromopropane. Now look at the right. Add peroxide. The whole mechanism changes to a free radical pathway, you form a more stable secondary free radical, and your product is 1-bromopropane. You have to know both the product and the intermediate for each case.
All right, let's hit another absolute exam hotspot, ozonolysis. Why is this reaction so important? Because it's a tool. It's like a chemical pair of scissors that cuts the double bond in half. This lets you work backwards. By looking at the little pieces you get, the carbonyl compounds, you can figure out exactly what the original alkane looked like. NEAT loves to give you the products and make you play detective to find the reactant.
We've now made it to the final part of our core concepts, the section that connects the world of straight chains to the world of aromatic rings. This is where we cover the one conversion that is super high yield and you absolutely have to know.
You know, here's another one of those subtle but incredibly important points that's just hiding in a plain NCERT paragraph. Not all the hydrogens on an alkene are acidic. Nope, only the hydrogens that are directly attached to a carbon with a triple bond. That's it. It's because that sp hybridized carbon is really electronegative. So a terminal alkyne, like but1-ine, is acidic, but an internal one, like but2-ine, not at all.
And this reaction right here, this is the ultimate link. The cyclic polymerization of ethene is just the most elegant way to step into the world of aromatics. You take 3 simple ethene molecules, you pass them through a red-hot iron tube, and out comes one perfect molecule of benzene. This is your gateway from the aliphatic world to the aromatic one.
So what makes benzene so special anyway? It all comes down to this idea of aromaticity, which is defined by Hückel's rule. For a compound to get the special aromatic label, it has to pass a 3-point check. It's got to be flat or planar, it needs to have a continuous loop of pi electrons, and, most importantly, it has to have a very specific number of those pi electrons. 2 or 6 or 10 or 14, it has to follow that magic 4n+2 formula.
Okay, we have covered a ton of ground. Now let's pull it all together and consolidate everything with a high-yield revision map. This is designed for that super fast recall you need right before the exam.
Think of these as your mental flashcards. When you see Wurtz reaction, you should instantly think higher alkane but only even carbons. See Markovnikov's rule, you think unsymmetrical alkene, major and minor products. Ozonolysis, that's for finding where the double bond was. And of course, cyclic polymerization, that's your ticket from ethine to benzene. These are just quick triggers for all the reactions we've covered.
And here they are, your final revision triggers. For boiling point, just remember, more branching means less surface area, means lower boiling point. For stability, staggered is always more stable than eclipsed. For addition, the big difference is the intermediate. Carbocation for Markovnikov, free radical for Anti-Markovnikov. For acidity, it's easy. Alkynes are more acidic than alkenes, which are more acidic than alkanes. And for aromaticity, never ever forget to count those pi electrons and check the 4n+2 rule.
So to finish this off, I'm leaving you with a challenge, framed just like a question from your NCERT exercises or the NEAT exam itself. An alkene, let's call it A, undergoes ozonolysis and gives you 2 moles of ethanol. What is alkene A? This is a direct test of your understanding of ozonolysis. Pause right here, work it out, and prove to yourself that you've mastered this stuff. You can do this.